my name is Touchet, and I'm excited to talk to you about the development of oxidatively responsive scaffolds in diabetic bone grafting applications. And this work is really motivated by the fact that diabetics have a limited healing capacity due to a high level of reactive oxygen species in the intercellular and extracellular space. This is molecules like hydrogen peroxide that promote more bone resorption than they do bone formation. And so one way to tackle this is to develop a material system that is an antioxidant in nature. What we have chosen to do is use a two-component system, a methacrylate and a thiol, that when reacted forms a mesh network that can act as an antioxidant. There are also several other components that go into choosing a material for bone grafting applications. One, we want this to meet the same requirements, mechanical requirements as bone. We want it to be biodegradable, and we need to make sure that it has the right amount of antioxidant behavior. And what we've been able to show through structure property relationships and varying different types of methacrylates and thiols is that we can come up with the right combination that gives us the stiffness of bone, is biodegradable and tunable at that, and we can have an antioxidant effect that brings us back into the physiologic range. The next step in this process is to develop a porous scaffold so we can have cellular infiltration and eventually lead to native tissue causing a bone fusion in these patients. And what we've been able to show is through emulsion templating, we're able to get highly porous scaffolds greater than 90% air of these polymers or this material, and there's a lot of interconnects. Furthermore, we've been able to show or demonstrate control over these systems through varying some key parameters, such as mixing speed. So as we increase the mixing speed, we can take these pore sizes from very large pores of 500 microns down to small pores of about 27 microns. Conversely, we can add additives to this system, such as stabilizers. And so if we have very little stabilizer, we can have even larger pores over 650 microns. And then if we add more stabilizer, we can reduce that down to about 350 microns. So this is really exciting work towards the steps of developing this bone graft. And the next steps that we're moving to is a rat calvarial defect model that will see how bone infiltrates into these scaffolds and if healing is actually occurring better than a control. So this is really cool work, and I'm excited to see it. It's also work being done out of Duncan Maitland's lab and sponsored by an orthopedic company in Novus. Thank you.